Okay, so we can begin. So again, any questions so far? Feel free to ask questions and so on. Okay, so let's begin by finishing our discussion on this energy momentum tensor. Okay, so remember last time we constructed it for a bunch of point particles. And we discussed that the energy momentum tensor in general is something like d tau, well, sum over all the particles, their mass, and then these four velocities is for each particle n, and a four-dimensional delta function. So first of all, anyone have any questions about this? It's okay? Yeah, sure. The m's here? Yeah. They can be different numbers, yeah. Like this m here is like if you have an electron, that's the mass of the electron. If you have a proton, you have the mass of the proton. You just add the appropriate masses. Or you include the appropriate masses. Right, and then we did a slight manipulation on this thing. And we used, I won't repeat it here, but you can trade in d tau for dt. And then the dt integral you can immediately do because inside of this is a delta t. So you can just integrate that to 1. So then you're left with a 3D delta function. The integral's gone. And I wrote it, I think last time, then dx mu dt, dx nu d tau. And I traded in one of these d taus for a dt. But then we can also, as a sort of step I did also last time, you can also use the fact that dx d tau is, by the chain rule, dx dt, dt d tau, right? So this I can write as dt d tau, and dt d tau is the gamma factor for that particle. Okay, so this is, let's just write that one out. Makes it a little more symmetric looking, which is good. That's the gamma particle for the nth, the gamma factor for the nth particle. So it's just determined by its velocity. And I remember now to put a little n subscript on gamma, the gamma of that particle. Right, so that is to say, gamma n, 1 over root 1 minus vn squared, is the velocity of that particle. Doesn't mean that you're doing any boosts at this point, okay? You're in a given frame, your clocks are x and t, but the different particles have different speeds. So it's a factor determined by their speed. And how on earth this thing knows about n? That's because secretly all these taus should have little n subscripts on them because every particle has its own proper time clock. So you should, technically I should put n's everywhere, but it gets a bit boring to write that. Okay. So last time we checked that this gave us the correct T00, the energy density, right? That was straightforward. So T00, well, let's just put it up here. T00 then is very simple because as we said, then you have dt's everywhere, which is just 1. So that all goes away and you have this. And this is indeed the energy density. I forgot my gamma factor. That's indeed the energy density for a bunch of particles. Because this factor here is the energy of a particle if you set c equal to 1. Right? M gamma is the energy. Let's just write that out to be explicit. It's the energy, kinetic energy, if you like, of the nth particle. And it's the energy density because it's localized by the delta functions. Okay, maybe it's useful also to define the number density of particles. So the number density, let's see, how would I write the number density if I have a bunch of point particles? What expression would I write for that? Right, number per unit volume. That's the energy density. What might be the number density? Yeah. Did you say big N or did you say sum? Sorry.
I guess either sum on all the n.
That's right. Yeah. Sum over n and then the delta function. Okay. So that's what a number density looks like if you have point particles. Okay. It's a bit of a funny distribution, but that's how it is, right? It's 0 and then it hits wherever the particle is. It can be a smooth number density that we might often think about. If you think about, say, a gas or something, you often like to talk about smooth densities. And that would come from some big region here. And maybe instead of saying, well, the number density of all my point particles is exactly that, that's the correct formula, I might say, look, I want to smooth this thing out. So maybe I pick little smaller boxes that house a bunch of particles. And I ask, what's the total number density, if you like, or I average this thing over some box here. And if it were to house, a billion particles or so, this will end up being a much smoother function. Okay, so you basically count the number in that box and divide by the volume of that box. That's what it would be. So, or said differently, you would just integrate this delta function over the size of the box and then normalize to the size of the box. But anyway, this is the exact statement. And so if I like, I could write T00, or the energy density. By 1, I could write this as the average of the energy of the particles in some region times the number density. Is that okay? Right, the energy density, let's just be clear. What you might mean by the average of a bunch of particles' energy would mean you would presumably sum them and normalize. And so it's something like this. If you were being exact, it's morally like this, except you might smooth over a box. So I'm not going to go into all the smoothing, but you kind of want to do a little bit of the smoothing like I described. Is that okay? That's what you would mean by an average, right? You weight them and then you normalize. Okay. So going the other way around, if you think of the smoothed quantities, this is just energy density over number density. And so flipping it on its head, the energy density, I could write as the average energy per particle times its number density. That's nothing very fancy, right? Energy density is energy density. I hope it's a simple idea. Is that all right? Okay, so these slightly more compact way of writing things than dragging around all the delta functions will, I think, will help us describe the other components of this thing in a little more compact notation. So any questions about that? Right. So we can play a similar game with the other components of this thing. So if I look at T0I, let's use this expression. Kind of probably the most convenient form of this thing, right? Again, just to recap why I bothered with this. I don't know about you, but if someone just hands that to me, it's kind of nice. There's T derivatives, there's no proper time and so on to talk about. There's gamma factors. I hope each piece is relatively simple to interpret. This thing is a bit more cumbersome. There's an integral over time and so on. You weren't expecting that in a 4D delta function. But the point is that this is manifestly covariant. And this is not so clear that it's covariant because you've got T and there's time dilation and so on. So you may not have guessed, oh, I should just put in 1 gamma factor, or maybe you should put in 2 gamma factors. I don't know. But anyway, this is correct because we derived it from that manifestly covariant answer. All right. So T0I then, we just put a dt, we get 1, and then it's dxi dt, which is a velocity. It's T0I. And so to be sure, this is Mn, the velocity of the nth particle. This is nothing fancy. dx dt is certainly the velocity. And then a gamma factor. And so what's this thing here? That's the momentum. Relativistic formula for momentum is good old mv with a gamma factor. So we recover what we were hoping for. We get the momentum of the nth particle. That's what this is. The delta function. And that T0I is, as expected, the momentum density. Okay, and if I want to use a similar notation to up here, where I say, well, if you're summing over there's some factor here times a bunch of delta functions, I can think of this as in this case, the energy density. This I could write, or energy times number density. This is some average of the momentum in the ith direction times the number density by the same reasoning. Okay. So good, that's our momentum density. And let me also just remind you that all I have really compared to that, all I have is this extra factor of V. So it's actually maybe useful to remind ourselves of that. This is also E times an extra V times that. It's just an extra V. Okay. Yeah, momentum is EV. If it's not obvious, but it is. All right, good. And then let's put this in a box. And then finally, we want to think about Tij. Okay, so I come back here, and now I'm going to have a dxi dt, dxj dt, so two factors of velocity. That's the only new thing. So I'll just write that down. Mn, two factors of velocity now. Gamma factor, delta function. And well, it depends how I want to write this, but yeah, I could write this then as like the average Mn. I don't know, let's put the gamma n up front, doesn't matter. Velocities times number density. Or again, this is the energy. We're just down by factors of V. So let me write it using that notation again. Number density. And the Tij's, if you recall from last time, we gave that a name. We called it sigma ij. Just a name for Tij, the spatial part of the energy momentum tensor. Okay, so that's the structure of this thing. We can put it on the board one more time. P mu nu, if you like, I could say is there's some number density. By the way, this can vary, right? So when I write n here, this can also be a function of space and time, right? So it's, if you do some smoothing, this would be the number density in that region, which might be different than the number density in that region, that region, that region, and so on. Okay. So for our starting point in cosmology, we assume uniform number density, but that's an additional assumption that I have not made on the board. Is that okay? I'm not assuming that they're clustered evenly, and it could evolve in time as well. We don't know. So there's a number density in all these factors, and then I can draw a big old matrix. Rho has the factor of the average energy per particle, and then these are weighted by the velocity, say in the, I don't know, one direction or the x direction, if you like. That should be a z. It gets a bit boring writing this after a while. Okay, those are the momentum densities weighted by a V. And then this spatial subblock is going to be two factors of V. So for example, this one is En Vnx squared, ij both equal to 1 or x. And I'll just summarize a few of these. Vny squared, Vnz squared. And then the off-diagonal pieces of this thing that I called sigma ij would involve Vx, Vy, and so forth. Okay, I don't know. I'm putting the X's and Y's up just because I have the N down. Is it all right? Those labels don't mean much. It's not sacred that you put it up or down. Is that clear? Those are just subscripts or superscripts to designate some meaning to these things. So Vx, Vz, and so on. Is it okay if I don't fill in the rest? You can easily do that. It's just X, Y, X, Z, Y, Z, Y, Z. Okay, so that's the matrix. So you can see if these particles, and to be sure, I'm setting units where C is equal to 1. Okay, so you can divide by C's here and there, and they all have the same units. So to be sure, if you have a system of slowly moving particles in non-relativistic gas, then you can see the hierarchy of this thing, right? You're going to be dominated by the energy density. These momentum densities are going to be down by a factor of V, and then the spatial part here is down by factors of V squared. So for slowly moving stuff, this is really negligible, and this stuff here is moderately negligible, and that will dominate. Okay. So now we want to say something about what the values of these things are if we impose our assumptions of homogeneity and isotropy. Okay. So, but any questions about this structure? Is everyone okay with this? So the diagonal pieces will be very nice. They're going to be related to pressure, as I'll elaborate on in a second. And then these are a little more subtle. Okay, but I'll just describe it in a minute. Okay, but the off-diagonal pieces will be associated with anisotropies in the fluid. But I'll come back to that in a minute. But let's have a think about, there are some pieces here. Let's start with these momentum density pieces. So there's the momentum density in the x direction, y direction, z direction. And we wish to now think about our homogeneous isotropic universe. And so in the homogeneous isotropic universe, the values of these things are a little bit very simple, but maybe slightly subtle. Okay. So we have some, let's say here's a chunk of the universe. Here we are at the center, let's say, as far as we're concerned. And there's all this stuff expanding around us, right? So there's stuff, if you look at a little patch over here, for example, so think of this as a gas of particles. So there's zillions and zillions of particles everywhere. In particular, there's a bunch of particles here. And they're moving out, right? Everything's moving out with the universe's expansion. And there's stuff here, which is not moving as fast. The further you go, the faster it moves. And so you would be forgiven for thinking that these momentum densities would be non-zero. Like if I'm here and I look at this patch of the universe over there, right? Think of them as particles, or you could think of them as galaxies, if you like, distant galaxies. Those distant galaxies over there are in a real sense moving away from us. So we would say they have a pile of momentum in that direction. We would think they have a bunch of momentum density, or they have a large velocity. But the sneaky thing we wish to incorporate is the fact that we study this in co-moving coordinates, as we discussed before. Okay, so in co-moving coordinates, it has the beautiful property that, so if you like, these velocities, they're defined by the x's that we're familiar with, right? So if you have a chunk of material sitting there and it's just moving with the flow of the universe's expansion, in co-moving coordinates, you assign a velocity to that of 0, these velocities. So so specifically, I mean, we could derive all this a little more rigorously than I'm doing. I'm just giving you an upshot. The way we have to use this object is we need to use these V's here as the velocities sort of relative to the overall motion. Does that make sense? So you could think of the V's here, they need to be measured relative to, let's say, the center of mass of this little box. That's the beauty of the co-moving coordinates. So if everything's just static but going with the flow, all of our V's are 0. That's what happens in co-moving. Okay. So co-moving coordinates. Effectively subtracts out the flow, or the Hubble flow, we would say. Okay, so a boring universe where you just say, oh, you know, like the picture of the raisins in the loaf of bread that's expanding, they're all, in co-moving coordinates, those raisins are all static. They all have these kind of V's equal to 0. That doesn't mean that all of our V's are 0, because if this is a galaxy over here, it has the stars, even relative to the center of the galaxy, the stars are moving. Okay? So we're not saying that the V's are literally 0, because not everything is caught up in the flow. And the air in this room is not caught up in the Hubble expansion. They're moving. Right? This motion is not related to the Hubble flow. Okay? The Hubble flow for stuff that's 2 meters away from me is basically 0. Okay, so the motion of the air in this room is all what we call peculiar motion. These V's are associated with some, I don't know why people call it that, but peculiar motion means the motion on top of the flow. Is that all right? So if, like over here in this little box I drew, there's stars orbiting around the center of a galaxy, the motion of that stars relative to the center of the galaxy, those are the kind of V's, right? We have not subtracted that out. We're just subtracting out the average velocity flow. Okay. All right. So now I want to claim that with all that being said, these are 0, even though I just told you the V's are not necessarily 0, because there might be some motion. Can anyone tell me, nevertheless, why those are actually 0? There's some assumption we made that makes them 0. Yeah.
If we assume co-moving coordinates, that those momentum terms will go in here because center of mass.
Center of mass is not. Okay, there's a key thing that I wrote on the board that we have to identify. What's the key ingredient in that statement?
That those entries correspond to momentum.
Those entries correspond to momentum. Okay, but let me say something here. So we have to do some kind of average over all these stars. And so the key word there, right, is the average, which I think is related to what you're saying, relative to the center of mass. But it's important to note that what we're dealing here are these kind of average velocities. Is that clear? So if you take a box here and you, thanks to co-moving coordinates, you're basically in the center of mass of the box, if you like, and you think you're at rest, and observer here is at rest. It's pretty much what you just said. Then relative to you, there has to be stuff moving to the right just as much as it's moving to the left. So you think, okay, there are stars moving that way in the galaxy, and then stars moving that way, and so on and so forth. Or it just is a gas of particles zipping around. And just like air in this room, the gas of particles that have some high speed, right? Things are moving at several hundred meters per second, the air molecules in this room. But we want to think that the air in this room is basically, we have no wind. That's the statement. Going to co-moving coordinates is like having in a frame in which there's no wind velocity, but the particles are zipping around fast. So just as many move to the right, to the left, up, down, in such a way that the average is 0. Okay, so isotropy in these co-moving coordinates has lots of implications. That's what we want to use. It implies that these averages are all 0. Okay, if we really were just standing here and there's a flow of a river or wind or something, we have to assign these things non-zero values. But in co-moving, we've deleted all that. All right, then we come to these pieces here. So let's have a look at this piece, for example, or let's say this one. So we'll look at these sigma, I don't know, for example, 1, 2, which is En, Vnx, Vny. This one doesn't necessarily have to vanish just because we subtracted out the Hubble flow. Can people see that? So let's say I go to the center of mass of one of these boxes, and then there's a little box that we look at, one of these boxes in the universe. We're in its center of mass. So for sure, the average velocities have to be zero. So if I start imagining there are particles zipping around here, and you might imagine, okay, some move that way, some move that way. It's just a random spread of funny velocity vectors. Okay. And it should be somehow those arrows average out to zero. The velocities we've said average to zero. Okay. Well, this weight factor of E is not going to spoil that. It's just a function of V squared. Yeah, so well, is that clear, by the way? The average of V is zero. This is basically, you could say it's zero because you're going to, if it's an even function, right, the probability distribution is even, the average of any odd moments is going to vanish. So average of V is zero, but E times V is also an odd function. It will average to zero. All right, so that's a system that would have an average velocity of zero. But imagine, just for the sake of argument, we could imagine a funny arranged box where the particles had funny speeds. So imagine, for example, you picked one and it did this. Let's call this the X direction and the Y direction. And then there was some other random particle like this, and then like that. You see what I did there? If I did it right, the average Vx is zero. Is that clear? I tried to do it. So there are just as many arrows with a positive Vx as there are arrows with a negative Vx. Let's see. 1, 2, 3, 4 of them are in the negative X, negative Y direction. And 1, 2, 3, 4 of them in the positive X, positive Y direction. Okay. So this has the property that the average of Vx's will be zero. It does this. But you see it doesn't kill this. Because this would be some weird system where you've correlated Vx and Vy. Okay? When Vx is positive, Vy is positive. When Vx is negative, Vy is negative. So therefore, this average would be non-zero. But this system that I just drew for you breaks something. What does it break in terms of our assumptions? It breaks isotropy. Okay, so this is clearly anisotropic. And in fact, in this way, all these off-diagonal pieces of the energy momentum tensor are associated with anisotropies in the system. Okay, so in a fluid, again, in fluid dynamics, you may meet this. You have to meet this sigma ij. And we talked about last time the local momentum density changes in relation to gradients of the stress tensor. It hits if you have some funny anisotropies in the system. So at the particle level, the particle velocities in different directions have correlations between them. Okay, so when we assume isotropy, then we yet again get that this is zero. You assume isotropy. Yeah.
The velocities for all have some sort of curl to them. Would that also break it also? Or would it break isotropy? Like, for example, stars moving around galaxies. Or are we considering these points to be galaxies?
That's a good question. I think it may be okay.
It looks like it'd be quite a few dimensions, 3 dimensions.
Yeah, I mean, of course, you then have to pay attention to the fact that it's going to rotate like this in some region. Then when you move over, it's going to rotate again. So You're going to see some sort of breakdown naturally of homogeneity as you move from one region to the next. If you want them to rotate this way, then they're rotating around some other centers again and again. Yeah. So really, since we're at the level of homogeneity and isotropy, of the level of large-scale structures, we want to think a little bit more about, like, say, motion, like galaxies and big objects, things like this. So if you saw the galaxies in the universe having that funny arrangement of velocities, you would have identified anisotropy in the universe on large scales, which we have not seen. Okay. I think last week, I forget the name. Anyway, someone at Harvard was claiming we do have evidence for anisotropy in the universe, but it's a controversial claim. All right. So all this does is reduce our energy momentum tensor. We're sort of heading towards the one we already claimed last week. Well, there's one more thing to say about now these diagonal elements. So these, for sure, we cannot claim as zero because they're the average of v squared. So the thing you're averaging is a positive definite quantity. So they cannot average to zero. But isotropy, yet again, is going to imply that they're all equal, right? It cannot be that the velocity, the x velocity squared should be different than the y velocity squared, etc. So they have to all be equal. And yeah, so these things we call the pressure. So okay, to get the full answer, I have to put an n there, the number density. And one way we like to write this, instead of singling out x's, y's, and z's, because it doesn't matter, because the average of them is all, the average of the squares is all the same, you can sum all three of them, right? I could write this as ENV squared. I add up x, y, z, so that's v squared, and then I have to compensate with a factor of a third, right? And I can put the number density there if I like. Now, last time we explained that these diagonal pieces, when you have isotropy, deserve the title of pressure. Even this is for a special, free gas of particles. But for a more general system, where there are interactions and so on, these spatial parts of the energy momentum tensor, we said deserve the title of pressure because we checked that the gradient of these pieces gives rise to changes in energy density, which is exactly what pressure does in a standard system. Changes in pressure generate forces. Changes in momentum. Okay, but for this ideal gas, or gas of point particles, here's a concrete formula for its value. And maybe I should put in a c squared just for once, to put in restore factors of c. And so, in fact, yes, this is a relativistic formula for pressure, if you haven't seen it before. We can check it has the correct non-relativistic limit that probably everyone has seen. So relativistic formula for pressure has that. It has a 1 over c squared floating in it. If I choose to write, if I include factor of energy. And then with all this being said, our T mu nu then, as promised, is rho 0, 0, 0. And then these pressure factors. Okay, so that's what we used last time as our source for the Einstein equations. And we can just see, you see these arguments of homogeneity and isotropy are enough to nail it to that form, actually. I've just illustrated it for you in the case of a collection of point particles. We could have a more complicated system and it would still collapse to this form. But for a more complicated system, our formulas for rho and p would be some more complicated formula than that thing there. And and the usual formula for energy density. All right. So perhaps, shall we check that this is a familiar formula for pressure? Does it look a bit unusual? Seen that formula before for pressure? Yeah, so maybe we can double check on that. Well, when I say double check, I mean we derived it, so that's the answer. But I just mean maybe we can do a sanity check that it connects to the non-relativistic result that everyone's probably familiar with. Let's think of an ideal gas. That's essentially what we're studying. It's free particles zipping around. Okay, so first of all, you would write, so we'll say recall. Pressure has the ideal gas law. PV equals NKT. There's one way of writing it. We don't even need the system to be thermal. Let's assume it's thermal as well, just to make it as familiar as possible. Okay, that's cool for everyone. So we'll write our pressure divided by volume. Okay, so we have the number over the volume, number density. Okay, so this is number density times kBT. All right, and then you may want to think about there's a kBT, right, for just ideal gas is related to the kinetic energy per particle, the average kinetic energy per particle. And maybe you can recall that it is literally the average kinetic energy. It's an mv squared, right? And there's a factor of a third. Do you remember that? So this is related to the fact that you get a half for energy, gives you a half kT per mode, right? So a half kT would be related to the kinetic energy, which is a half mv squared. So you see how the halves cancel. And then you have to do per mode. There are 3 modes, X, Y, and Z. Okay, so the energy would have an extra factor of 3, but I'm giving you the temperature, so I have to go backwards and divide by 3, if that makes sense. Anyway, so this is the formula for that. And now let's check our formula, which is the one up there, the relativistic formula. So we have this thing, and now I have to use the content of saying it's non-relativistic. Non-relativistic says that the energy is just mc squared. Well, let's assume all particles are the same mass for simplicity in this discussion. So then that pressure is N over 3 mv squared. Okay, so well, it's clearly the same thing, right? Is that all right? You just write mc squared and then it collapses to that formula. Okay, so these match. Okay, so any questions about this? So again, if you wanted to take the relativistic extension of this and someone put a gun to your head, you say, oh, maybe I'm a factor. You would be correct because that is the right formula, but that would be a bit of a guess. Okay, now I want to say something. I should say something then about curved spacetime because we've essentially done all these calculations in flat space formulas. With just some commentary as to what must happen when you use co-moving. So only just say a couple of words about this because I don't want to do too much GR in this course. But let me just state for you that in curved spacetime, you can update this nice looking formula. And here was our formula as covariant a form as possible. And the update, if you have curved space-time, is pretty nice. You just divide this by the square root of the determinant of the metric. That's it. That's the only update. And the reason for that, and again, if you haven't studied GR, it may not be familiar to you, but don't be too scared. We're not going to use this too much. Let's just state that the natural measure on an integral, in fact, this is a general fact, is for a 4D integral is the square root of the determinant. So when I say it's general, I mean, even if you were doing flat space and you wanted to just change coordinates from Cartesians to sphericals, you know that you can't just write integral d3x, let's say you're doing 3D. You can't write integral d3x equals integral dr d theta d phi. It's wrong. There's a Jacobian of the transformation. Right? There's some r squared sine squared theta. You can check that that's exactly root of the determinant of the metric. Okay. And so I divide throughout by that here, so that if you now integrate this thing, the root g's cancel, and then you get the integral d4x of a 4D delta function, which is 1. And everyone can agree upon that. And then the t mu nu, which I quoted for you, if you recall a couple of lectures ago, I lowered an index. That means you have to write g nu alpha of this thing. Well, let me not write out the whole thing. I'll just write it as t mu alpha. That's how you lower an index. Maybe I'll put this on the homework, that you can check that this gives this thing with nothing other than a boring minus sign, even though we have a slightly interesting metric. Okay. If you had a Minkowski metric, the Minkowski metric, whenever you lower, just gives you some minus signs, because Minkowski metric is 1 minus minus minus, so you're just going to flip plus the minus. And this works too in this curved spacetime. You can check that on the homework. The update is very simple. Yeah, so you can do this even though our metric, has ones and has a squareds in it, has r squareds and sine squared theta and all that good stuff. None of that matters when you self-consistently construct t mu nu. It all collapses to this. Questions about that? No, we need homogeneity anisotropy for it to collapse. If they're intrinsic anisotropies, there's off-diagonal stuff. There's momentum flows, off-diagonal stuff. Yeah. So the key point, if you like, the homogeneity anisotropy, those principles are enough to nail it in terms of these two numbers, rho and p. And the mixed t mu nu presents it in its simplest form. That's the only thing. But if you have other stuff, other physical stuff, right, like anisotropies, we cannot delete it by raising and lowering indices. Those are real things that will survive. But it tends to be that upstairs mu, downstairs nu packages it in its simplest possible form. Let's put it that way. If I was to give you some maybe intuition for why t mu nu is morally the nicest thing, okay? I mean, we're just raising and lowering. So asking, I mean, there's a certain sense in which this one's slightly more fundamental than that one. That's a bit of a funny thing to say, because I can move to one to the other by raising. So who's to say what's more fundamental than the other? But let me make one comment. Okay. So if you were studying, let's put aside GR for the moment. Let's say you were studying some condensed matter system, okay? And you have a condensed matter system, and it has a homogeneous isotropic stuff, but I'm interested in studying perturbations on top of that. Okay, so that's what I want to study. So there's something interesting to study. As long as your background has, translation symmetry, in fact, I don't even need isotropy. As long as the background has translation symmetry in space and time, there's a conserved energy momentum tensor. That's not something about GR, right? Any system that has time and space translation symmetry, there's a conserved energy momentum tensor. Okay, now the natural way of writing that energy momentum tensor is in fact this, T mu nu, for a reason I'll explain in a minute. Okay, that particular combo. Okay, so it exists, as I said, any system with time and space translation symmetry. Okay, you don't even need to say the word relativity. You could have condensed matter system, which is broken boost invariance, right? So there's a preferred frame, but that thing will still exist. And it's conserved by the Noether theorem in the way that I've written it, d mu, and you contract mu with mu. So it's conserved in the sense that that's zero. That's still true, even in a condensed matter system. You don't need to know relativity. This is dt, and then the i's are dx's. There's no factors of c. Okay, so well, this is dt, not dct. This is true in a condensed matter system. If you have homogeneity, if you have translation symmetry. And now I've the only thing I've done is I've had this floating mu index and I've put it down. Okay, so this may or may not upset you, but remember this thing is, there's a conserved quantities associated with this, right? So it's the time component, T0, with a new index. Remember, those are the ones that are conserved, right? Is that okay? The time component, mu equals 0, those are conserved. And this we would call the form momentum. And that form momentum naturally, therefore, is the downstairs form momentum. Okay, so you say, well, what's the big deal? If I had to put this upstairs, you would have written a form momentum upstairs, which maybe you're slightly more familiar with in, say, special relativity or some context. Yeah, special relativity. But I put it downstairs. The sense in which this object is slightly more fundamental is that P momentum is the conjugate variable to X, right? They are paired. Okay? These variables come in conjugates. And X lives upstairs. I'm sorry, that's how it works. That's where everything begins. We choose to put an upstairs index on X. That's just the starting point. Okay? So once you have that as your starting point, its conjugate variable comes downstairs. That's how it works. So the slightly more fundamental object is this. So it's the integral of the one with the downstairs index. So anyway, I'm not explaining directly why it leads necessarily to things looking simple, but maybe it gives you a clue that we're starting with a slightly more fundamental object. Okay. So yeah, people don't like this one because, right, this P lower nu would be like energy, comma, minus P. There's a damn minus sign, but it's actually more fundamental. All right, anyway, questions about this? All right. That was a long way of saying this is the energy momentum tensor for a homogeneous isotropic universe. Okay, so now I want to do some important cases of this thing. Okay. Relevant to cosmology. Okay, so we basically already did this, but I want to highlight a point. So if we have non-relativistic stuff, which cosmologists like to just call matter, okay, then as we've just said, the pressure is just down by some factors of v squared. Energy density is En. Okay, so non-relativistic matter just means V is much less than C. Okay, so the peculiar velocities, okay, the velocities of the stars in the galaxy, again, we've said, not the Hubble flow. That velocity is small compared to C. So if you're looking at stuff that has that property, then this pressure here is basically V squared over C squared, and even a factor of a third smaller than rho. Okay, so V much less than C implies P much less than rho. And so for such situations, you can see the T mu nu collapses once again to rho and a bunch of zeros. So for example, in galaxies today, the typical speeds, relative speed of the stuff in the galaxy, the gas and the stars, is from about 10 to the minus 5 to about 10 to the minus 3 C. Okay, bigger galaxies, it's like 10 to the minus 3, and smaller galaxies like dwarfs, it's down to like 10 to the minus 5 and so on. So you see it's much, much less than C. And the relevant factor is actually V squared over C squared. And even a third for good measure. Okay, so V squared over C squared is something like 10 to the minus 10 or 10 to the minus 6. The pressure is much, much, much smaller. Okay. And maybe just to recall, in the, say, the second Friedmann equation, A double dot over A, remember, is minus 4 pi G over 3 rho plus 3P. You have to compare P to rho. Okay, you're directly comparing P to rho. So this is relevant. So here we have this fact that this is much, much smaller than this. So that will be very important in helping us simplify these equations. Okay, now there's an opposite limit, which is just as important. We could just call it, well, we might call it ultra-relativistic matter, but people already use the word matter. Okay, usually call it radiation. So here I have in mind stuff is either moving incredibly close to C, or it's literally moving at C like photons. Okay, we can dump them all into the same category. So here V is equal to C or near enough to C. Okay, like neutrinos in the early universe were moving very close to C. So they would fall into this category as well. So then if V is C, then the pressure formula, well, these C's just go away. So we just get the average energy, and there's a third. So the pressure is 1/3 of the energy density. Yes.
So are the only possible relativistic, stationary and ultra-relativistic?
Essentially, yes. Good question. That's right. So we'll talk a bit more about that in maybe next week, but there's a very good reason for this. So you can have a particle, like actually if we go really, really far back, even electrons and so on were relativistic or ultra-relativistic for a while in the very early universe. And then there's a transition where they drop and then they start moving at speeds v that are much less than c. And whether you're down at v of 0.1 c, it's already pretty close to being irrelevant, because then you got to take a 0.1 squared. You're already at a point where if v is 0.1 c, oh, we don't necessarily care about a 1% correction to this equation. And then for good reasons, as we'll explain, it just keeps on dropping. And it goes from 0.1 down to 0.01, 0.001, and so on and so forth. So there's a relatively narrow window in a certain sense that we can talk about later, where its v is like, half c, something like that. I'm not saying it doesn't happen. Electrons will transition from near C, pass down towards zero, but that window of transition is relatively small in time. So yes, we do get to pay attention to these two limits and get away with this pretty well. There are some cases when you have to be a bit more careful. All right. So yeah, so we should think photons for sure, neutrinos, at least in the early universe. Electrons, positrons, so on in the very early universe. We can talk about that stuff later. Yeah, and why I say neutrinos only in the early universe, we can talk about that too. Why not today? Now, it turns out to be useful. So generally, to solve the equations, right, we have a p and a rho. And we need to know the relationship between p and rho, as I've been sort of summarizing for you here on the board. If you have a much more general system, right, maybe you have an interacting system, not just a free gas like this, you need to then figure out how p and rho are related if you want to start solving these equations. Okay. Now, this is a very familiar thing. If you have some fluid, some system, you can't make progress if you do not know how the pressure and density are related to each other. You're just kind of stuck. So you need a relation between them, which is usually called an equation of state. Involves pressure and other thermodynamic variables. And in fact, most equations of state are not of the form that we're about to write, but this form that we're about to write is useful in many contexts in cosmology, though not all. So guided by this, we're going to imagine the equation of state has the property that the pressure is just proportional to the energy density, and the prefactor is called W for some reason. So the equation of state that we're going to choose is where this W is a constant. And this turns out to be remarkably useful. Okay, but be warned, this is not a general fact of nature. That's not by itself a deep property of nature. This happens to summarize some important stuff. Like, for example, if you wanted to study the internal structure of a neutron stars have lots of pressure. So, okay, it's not quite this equation, but there are related equations you'd have to solve in general relativity. The pressure matters. And the relation between the pressure and the energy density is not that. In fact, first of all, A, it's not really known. And whatever it is, it's sure to be more complicated than this thing. So some people try like rho to some power. That's a common thing where the power is not one like this. But this will work for us. As you can see, they already have two examples that kind of fit into that category. Certainly the second one does. Okay, so you specify if you trust on that form of the equation of state, you've specified the system if you pick a value for W, and then you can solve the equations. Any questions about that? All right, so maybe it's, I hope, obvious from the way I wrote it on the board, but let me just say what I mean. For this non-relativistic case, okay, again, there's nothing fancy. There's non-relativistic cases for the history of the universe, stuff like stars, planets, gas, the dark matter, we think also falls into this category. Yeah. Let me just say, so it's even the dark matter seems to be in this category. And yeah. Ah, good. Yeah. So that would be a good starting point. Right? If you use Fermi, so like a degenerate Fermi ball of stuff, that would give you a formula like this, except there's an exponent here, which is again not one. That's already why this formula doesn't work. I think there the formula is 5/3 or something. But more generally, most people think that's not a great model for a neutron star anyway, because there's like a quark-gluon condensate at the center and so on. So we cannot really treat it as a gas of free fermions. Yeah. But that's at least a better effort than this, which was a gas of free classical particles. So there we have a gas of quantum particles, and that will do better than this. Yeah. But yeah, I mean, I think those tend to give answers. It turns out if you solve the Einstein equations for that model, you get like that the maximum mass of a neutron star is, I think, 1/10 of the observed mass. So it doesn't work that well. There's a good discussion of that in Weinberg's old GR book. But yeah, you have to do a bit better. All right, so for non-relativistic stuff, right, so we say the pressure, all we need to remember is it's much, much less than rho. And at this point, as I said, we're not going to pay too much attention to whether it's the ratio of them is 10 to the minus 10 or 10 to the minus 6 or whatever. We're just going to treat that as essentially 0. So here we get away with W of effectively 0. Okay, call that an equation of state if you want, just says P is 0. And so then all this matter. And then the ultra-relativistic or radiation, I forgot to say, people usually call this radiation, right? Because the thing that comes to mind are photons, and some old people called photons radiation back in the day. We said that P is 1/3 rho, so W is 1/3. Okay, so those are the important numbers. And let's see, how are we doing on time? 10:03. So Yeah, I can, maybe I'll squeeze it in here since we're at this point, but there's a big discussion to be had on a type of thing which is completely not at all modeled by a bunch of classical point particles. In fact, you can see here, by the way, that the W value, right, you see it's anywhere, V has to be between 0 and C. So you would say that W has to live its life between 0 and a third. Right? We've kind of maxed out the two extremes. That you would think should be W. But then something, you can imagine stuff that's not described by an ideal gas, that's completely different from this kind of analysis, has no a priori reason to be modeled by this equation, as I said, but there's a very important case that actually it is modeled by that equation, even though it's got nothing to do with an ideal gas of particles. And that goes by many names, but I just put on the board. One name is called vacuum energy. And another name is the cosmological constant. And it's maybe the same as dark energy. But what I'll write here is the actual equation for this stuff, if I'm agnostic as to whether it definitively is the dark energy. It probably is, but we don't know for sure. Anyway, that's a whole nother discussion for later in the course and maybe for years to come. But let me just summarize that, funnily enough, it can be written in this way, and it has the property that the pressure is outside of this range completely, and it's in fact minus rho. So this would have a W of -1. Okay, so why there's a kind of sensible, in some sense, sensible thing to talk about that has these properties is something we can discuss later. Okay, I don't want to get into that right now with like a few minutes to go in the class. Now, once you have this, there, as I said, we can solve the equations. And the first kind of equations I want to solve, I don't want to directly solve this one. It turns out there's another equation that's super useful that we have yet to describe. Okay, but first of all, any questions about that? Okay, so I want to remind you once again, well, I just erased one of them, but the Friedmann equations. And let's do the case of a flat, spatially flat universe. I'll set k to 0. Because we've already said that the curvature is incredibly tiny, at most 1 pi 10 to the 3. Okay, so let's just delete it altogether for the most part going forwards. Okay, so then the first Friedmann equation, right, is Hubble squared, or A dot over A squared is 8 pi g over 3 rho. I won't bother with the c squareds for the moment. And I've deleted the curvature. Well, I would go there. And then the second Friedmann equation, which I had on the board a minute ago, is A double dot over A minus 4 pi g over 3 rho plus 3 k. Is that all right? So we derived these a couple of lectures ago. This pair of equations is perfectly fine, and we could just drag these around. But they have lurking in them a formula for the evolution of rho itself if we do a little bit of manipulation, which turns out to be quite useful. Okay, so what I'm going to do is take the time derivative of equation 1. If I do that, I'll get a rho dot, right? So that's why I want to do that. So let's take a time derivative of this thing. So the right-hand side is going to be easy. That's just 8 pi g over 3 rho dot, time derivative. And then I have to take a time derivative of this stuff. I've got to take A dot over A squared, take a time derivative. So it's a little bit of product rule, whatever, on that thing. So if you differentiate the numerator, there's a 2a double dot and then an a dot over a squared. Right, that's from differentiating the a dot piece. And then I have to differentiate the a downstairs. So I get a minus 2 a dot. There's already 2 of them, so I'll get another one. I get a dot cubed over a cubed. Is that all right? That's what I get. That's the derivative of that thing, or the derivative of Hubble squared is that slightly ugly looking thing. And I want to do this because you see a double dot, I have a formula for a double dot. It's this stuff. Okay, so now what we want to do is try to eliminate that. So let's first, maybe I'll divide throughout by 2, rewrite this as a double dot over a dot over a. Okay, so you see that I'm just going to divide by 2. That's a super easy step. And then this leaves me with an a double dot over a times an a dot over a. But remember that a dot over a is just Hubble, so that we can just write that if we want. And then this term here is actually Hubble cubed, which I'm going to write as h squared times h, because I want to. Is that all right? All right, so now you have to, here, you insert equation 2. And here, when there's an h squared is 8 pi g over 3 rho. So now here you insert equation 1. Okay, so you just feed them into each other. We can just do that on the board, I guess. I get minus 4 pi g over 3 from that first term, rho plus 3p. And there's a Hubble left over. And then the second term, 8 pi g over 3 rho and a Hubble left over. And then the right-hand side is this with the dot. That's what I get. And it actually simplifies a lot. For example, these 3's, I'll get rid of them. You can divide by the 4 pi g's, cancel that, cancel that. This will leave you with a 2. And then on this side here, there's 2 terms that involve rho that you can combine, and then there's 1 term with a p. And so it's very simple to see that this collapses to rho dot is minus 3h rho plus p. Check that last step of algebra if you wish. Well, you should. And so this tells us how the energy density evolves. Okay. So naturally, the minus sign indicates that, as the universe expands, things tend to want to become more and more dilute. So energy densities want to drop over time, typically. But, and if we ignored the pressure, we can check that this 3 here will guarantee that the universe will drop in the usual way. It's related to things just dropping like 1 over volume. Maybe we'll pick that up next time. But it also tells us that if you have a lot of pressure, and say positive pressure, somehow this stuff wants to dilute even quicker. It wants to drop very fast the more and more positive pressure you have. But somehow for negative pressure, and like we have this case down here, see P is minus rho, you can already see that's a very special case, because that would be the case in which this right-hand side vanishes. That means that rho dot is 0. That means rho is a constant, only in that third case. Okay, so that's very closely tied to the fact that it's called a cosmological constant. It would be constant over time. But the other cases, it's going to drop over time, because this thing is positive, so there's an overall minus sign, but they'll drop at different rates. Okay, and I don't think I'll have time to do that now, but we can do it next time. Any questions about this? Yeah, and then we can maybe talk about the thorny issue that if energy is changing, what the heck is going on? Okay. All right. See you later.